Hello. In this video, I want to discuss graphing square root and cube root functions. We'll discuss the parents of these functions and then graphing them with some basic transformations. So first off, let's remind ourselves of our basic transformations. We have a table here, and this looks at how this will work with square roots and cube roots, but also quadratics, which is the first thing we really dealt with when talking about transformations. So our parent function, the idea of a parent function is it's the simplest version of that function. The simplest quadratic is y equals x squared. The simplest square root is y equals the square root of x. Or we could write that with rational exponents and say x to the 1/2. Cube root would be y equals cube root of x. And so on we'll have as we talk about parent functions throughout the rest of the year. Now, there is a small set of transformations that we talked about. They are reflection in the x-axis, vertically stretching or compressing, and translating left and right, so horizontally, or up and down, or vertically. Now we've seen how all of these work for the functions we've studied to this point. If I want a reflection in the x-axis, I put a negative in front. To vertically stretch or compress, I will multiply by some factor out front. I know I have a stretch based on if this number is in fact larger than 1, and I have a compression if this number is in fact between 0 and 1. And then to translate left and right or up and down, I put in some numbers right here. We note this is always written as minus h to indicate that when I do go left and right, to change the x, I put it inside with the x, and I always remember there's this opposite sign business that happens where if I saw x minus 3, my brain wants to move that 3 to the left, but it's actually going to move it 3 to the right. So this is how this works for a quadratic. How this will work for a square root or cube root? Well, essentially, you're putting things in and around the square root or the cube root, the radical. To reflect, I put a negative in front of the radical. To vertically stretch or compress, I will put some factor in front of the radical. And then to translate left and right, I will put something inside the radical with the x. To translate up or down, I will add or subtract something at the end. And again, the same rule applies. Horizontal translation, that sign will be opposite, whereas a vertical translation, the sign is exactly what you expect. So if I saw a plus 5 down here, that would in fact mean 5 up, 5 in the y direction. So to be more specific, here's a couple examples. Right here I see f of x equals 2/5 x minus 6 squared minus 2. So the first thing I'm asked is what type of function is this? Well, I notice there's no radical, and I see there is a 2 here. Power of 2 indicates that this is in fact a quadratic. Power of 3 would be a cubic, power of 4 would be a quartic, but this is a quadratic. Its parent is y equals x squared. What are the transformations I see here? Everything here that is different from x squared means some transformation has occurred. What do I have out front? I see a positive 2/5. So that means that there is a vertical compression. So this has been vertically compressed by 2/5. And minus 6 and minus 2, well, x minus 6, I know that means I will go 6 to the right. So I will say I have translated or shifted 6 right and 2 down. This problem right here, again, we're going to talk about a square root function in a second, but the way the transformations work is the same as we have been discussing throughout the year. The negative, pardon me, let me fill the rest of this out first. This is a square root function whose parent is y equals the square root of x. Now back to the transformations. This negative out in front means that I have been reflected in the x-axis. So reflect in the x-axis. The x-axis is horizontal, so to reflect in the x-axis, things go top to bottom, bottom to top. They're being reflected kind of downwards or upwards. The negative is a reflection. The 3, since 3 is larger than 1, this indicates I have a vertical stretch. And then this +1 and this +7 indicates I have shifted the graph. Horizontally, I've shifted the graph 1 unit to the left. Again, that opposite sign business. And 7 units up. So again, that's just a quick review of transformations and what they mean. This is something that comes up throughout Algebra 2, so hopefully it's as clear as it's ever going to be right now. How will we graph specifically the square root function and its parent, more importantly? Well, let's explore y equals the square root of x by making a table of values, a table of inputs and outputs. I'll do that right here. I'll put down x, and y will be the square root of x. Now, I could, in theory, just put in anything. If I'm exploring a function, typically I might start with something like -2 to +2, so -2, -1, 0, 1, and 2. I don't need to do quite that much. I'm going to go ahead and write down -1, and I'll hold that there for a second. And I'll put down 0. What's the square root of 0? Well, the square root of 0 is 0. How about 1? What's the square root of 1? That'll be 1. Now I could go ahead and list 2, but the square root of 2 is not a nice number. It's approximately 1.414. What would make more sense if I'm trying to make nice points is to pick perfect squares. So I have that 0 is 0 squared. I have that 1 is 1 squared. I know that 4 is 2 squared. I know that 9 is 3 squared. So those would be some good points to help me graph this. Now I left -1 up there at the top. Let's think about what happens there. What is the square root of -1? As you might recall, the square root of -1 is what we define to be I, the imaginary unit. When I am graphing, there are no i's in here. So as a result, this is not something I can deal with. Naturally, what's going to happen with a square root function is I will only be able to put in certain values, because if I square root a negative number, I get something imaginary, which I cannot plot. So let's look at the points we do have to plot. We have 0, 0. Every parent function we've seen to this point has gone through the origin. We have 1, 1. We have 4, 2. And 9, 3 is going to be a little bit off the graph. It's somewhere right here. So what will we see here? We see this gentle curve. Now, as I said, 0 is the smallest thing I can take the square root of. If I go below 0, I have a negative number. The square root of a negative number is imaginary. I cannot go below 0. So what I'm going to do is get this graph, which has this little terminal point right here where it just stops. And what I get is a bunch of points along this curve in this direction, just emanating infinitely. This will go up slowly, not very fast, but it does keep going up. Eventually I'll get to 4 when I take the square root of 16. I'll get to 20 when I take the square root of 400, and so on. Couple things to note about this function. The domain is naturally limited or restricted. Again, that's because square root of a negative is imaginary. Which we know is a problem. I can't graph that in here. If the graph looks like a parabola going sideways, well, that's because it is. Think about it. If I took a parabola and drew it sideways, I would see something that looks like this. Now the problem with this, if I had this up here, is this is not a function, because I have vertical lines that hit it multiple times. So essentially what happens is, in coming up with this function, I restrict to only the upper half of this little sideways parabola. That's what this is. It's the inverse of a square root function, or excuse me, of a square of a quadratic function, but it's only that upper part of the inverse. Okay, Let's take a look at some examples with transformations. So here I have f of x equals the square root of x minus 5 minus 3. So what are my transformations? I see this minus 5, I see this minus 3. This is inside with the x, so I know that means I will shift in the horizontal direction to the right. Minus 3 means I will go 3 down. Now really, once you understand the function, you can figure out the domain and range based solely on knowing those transformations, but we can go ahead and plot this. So what you might do sometimes with some of these problems is not a requirement, but it's certainly helpful a lot of the time, is to go ahead and plot the parent function. So the parent function, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. That's my parent function. I need to go 5 to the right and 3 down. So if I go 5 to the right and 3 down, that will put me right here. And this will be my new little terminal point. My curve is going to emanate, shoot out of this point. So I can move all these points one by one, but really the idea of using parent functions and transformations is to recognize that there is a pattern. The square root function, square root of 1 is 1. So if I go to the right 1, I go up 1. The square root of 4 is 2. So if I go to the right 4, I would go up 2. And that's just off my grid. So I'll get a graph that looks something like this. And try and make it look curvy because it is going to essentially flatten out some. But that's generally what it looks like. All right, we are asked for the domain and range as well. Well, on this curve, the smallest x value is 5. If I put in 5, I'll have the square root of 0. Anything lower than that, I'll have the square root of a negative number. The largest x value, well, this keeps going to the right. Or rather, I can put in very large values of x, and I can still square root those numbers and get a real answer. So my domain is bracket 5 to infinity. How about my range? Well, the smallest y value is negative 3, because again, the smallest this square root can be is 0. So that means my smallest y value is negative 3, and from there, all points go up. So I'll go negative 3 to infinity. How about the next example? Here, what are my transformations? Well, I see two things that are different from just having the square root of x. There's a 3 in front, which means I have a vertical stretch by 3. And the minus 6 at the end means I go down 6. So again, I can plot the parent function. Might be helpful. 0, 0, the square root of 1 is 1, the square root of 4 is 2. What am I going to do? I'm going to go down 6, but here's the tricky part, the stretch by 3. If I go down 6, 1, 2, 3, 4, 5, 6, puts me right here. What will happen? Well, the idea of a vertical stretch by 3 is I'm stretched. I would rise faster than normal. So where in a normal square root function, as I go 1 to the right, I go up 1. Here I go 1 to the right, and I go up 3 times as fast. I'll go up 3. Where I would normally go 4 to the right and up 2, I will instead go 4 to the right and up 3 times as much, which is 6. And I'll keep going in this fashion. The next point right over here, if I went 9 to the right, I would normally go up 3, but since it's stretched, I would go up 9. But these 3 points are probably enough to get a decent graph. Just try and connect it with a nice smooth curve. Notice that stretch makes it much less flat. What are my domain and range? Well, my domain is 0 to to infinity. The smallest value I can put in for x is 0. What about my range? The smallest value that y can take is -6. And then from there I will have larger and larger y's. Okay. Let's do one more example, and we'll talk about cube root functions. Here, I wish to graph the function h of x equals negative the square root of x minus 1 plus 4. So, as I'm doing this, I have to think about this carefully. I can see that I have a reflection in the x-axis. I can see that I am translating 1 to the right and 4 up. So I need to use that when I'm graphing this. Again, I can graph the parent or not. It really doesn't matter. What I need to know is the pattern I am using here. If I go 1 right and 4 up, that will put my little terminal point right here at 1, 4 because I'm moving from the origin. I'll go ahead and plot the parent so you guys can see it again. So I go 1 right and 4 up. Now here's the trick. There is a reflection. The reflection is going to make it so rather than going up, I will in fact go down. So where from that end point I would normally go 1 right and 1 up, I will instead go 1 right and 1 down. Where I would normally go 4 right and 2 up, I will instead go 4 right and 2 down. And you're going to see this will cross over the parent function that I had. And just put a nice smooth curve through it. The reflection will make me go down where I would normally go up. And if there were any points where I'd go down for a different function, that would mean down becomes up becomes down. All right. I'm asked for the domain, range, and intercepts. So for my domain, the smallest x can be is 1. I can get larger from there. Now for your range, think carefully about this. The smallest that y can be, well, it's not determined by this endpoint because these points down here are going down. So this is going to go down continually. Not fast, pretty slow, but it will keep going down. So my range has to go from the smallest y value, which is very, very small, up to the largest y value, which we can see is positive 4. Now this question also goes so far as to ask you about your intercepts. We'll recall how you find intercepts. To find a y-intercept, we make x 0. If I make x 0, I will have the square root of -1, which we know is imaginary. And we can see this on our graph. There is no y-intercept. It doesn't touch the y-axis. How about the x-intercept? I can see this is going continually down, but I cannot see where the x-intercept is. Remember, x-intercept means that y is 0. So this goes back to the little bit of solving that we have done. We'll do more solving next class. If I solve this equation, what will I get? I can divide by the negative and get that 4 is the square root of x minus 1. Well, if 4 is the square root of x minus 1, that can only be true if this is 16, because 4 is the square root of 16. Essentially, we're squaring both sides, which will mean that x is 15. And our our x-intercept is 15, 0. There will be more on that when we do more solving. Okay. So hopefully through those examples you get the idea of transformations, how that's going to affect the graph, and generally what the square root graph looks like. What about a cube root function? Well, a square root function is the inverse of a quadratic. Cube root function is the inverse of a cubic. Once again, I will pick convenient points. It was convenient to pick perfect squares when doing the square root. It's convenient to pick perfect cubes if I'm graphing the cube root. So I'll put 0 in the middle, and then I'll put some cubes around it. The cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is 2. How about negative numbers? Well, recall the cube root of negative 1 is simply negative 1, because negative 1 cubed is in fact negative 1. If I cube root a negative number, I simply get a negative number. So let's take a look at what this looks like. I could keep going. My next cube would be 27, but that's generally not going to be something you're going to be plotting. I go through the origin. The cube root of 1 is 1. The cube root of 8 is 2. The cube root of negative 1 is negative 1. The cube root of negative 8 is negative 2. So what I'm going to get here is a function that basically goes kind of sideways and has sort of an S shape to it. So this is a very recognizable graph. That's the idea. Our graphs are all recognizable in one way or another. Some more so than others. This looks very different from other things we've seen. How would this work if I included some transformations? Well, let's take a look. Here I have the negative cube root of x plus 1 plus 3. So I can see that I must reflect an x. I can see that I will go left 1, and up 3. So left 1 and up 3, that tells me where that center point is going to be. Left 1 and up 3 will put me right here. Now here's the deal. Where I normally go up on the right side, since I'm reflecting, I will be going down. My cube root, normally I go 1 to the right and 1 up. Instead I would go 1 to the right and 1 down. Normally I would go 8 to the right and up 2. Instead I will go 8 to the right and down 2. Can do the same thing on the other side. Normally I would go 1 to the left and down 1. Instead I go up 1. Normally I'd go 8 to the left and up and down 2. Instead I will go up 2. So it'll put me somewhere off the grid. And I just want to put a curve through it, a roughly smooth curve. Get that nice S-shaped curve. Wasn't asked, but of course we can discuss domain and range. The nice thing about the cubic, since I can cube root any number, and every number has a cube root, essentially that's going to force it so my domain and range for any basic cube root function, both of them will be all real numbers, or negative infinity to infinity. Do one more with a stretch. Excuse me. I can see this 5 is a vertical stretch. And I can also see that I have gone 2 right and down 3. So, normally I would start at the origin. If I go 2 right and down 3, that puts me at 2, -3 as my center. Now there's a vertical stretch by 5. So again, I think back to the points, I'll even write it out, apologize. I think back to the points of my parent function. Not 2, 8. Thinking about the other side. If I'm stretching, then that means each of these outputs will be multiplied by 5. So I have -10, -5, 0 will stay 0, 5, and 10. I am stretching vertically, meaning I will rise faster. Normally I would go to the right 1 and up 1. Instead I will go to the right 1 and up 1, 2, 3, 4, 5. Normally I'd go right 8 and up 2. Instead I would go right 8 and up 10, which that's a little bit off this grid, excuse me. But I can still approximate where it is. If this is 2, 8 to the right will be about 10, so this will be about here. Normally, I'd go to the left 1 and down 1. That's what this -1, -1 tells me. But instead, since I'm stretched, I will go to the left 1 and down 5, which will put me here. So what will I see? Something like this. I see a stretched cubic, which again looks more S-like, more like a snake going through the grass. Okay. So that's the essence of graphing these things. Make sure you understand the transformations. Make sure you understand how to identify the different graphs. The last problem I'll give you here, if you're asked to write an equation, if I ask you to write the equation of a square root function which has been reflected in the x-axis, vertically stretched by a factor of 3.5, translated 7 units to the left, 2 units up. So you want to start off with the fact that you have a square root function. Now it must be a function, and it says an equation, so you need to say y equal, or f of x, or g of x, or something, not x or some function of x. And it's a square root function. How do I put all these things in there? There's a reflection in the x-axis, which I know means I need a negative out front. To stretch by a factor of 3.5, and that is a stretch because 3.5 is larger than 1. To go 7 units to the left and 2 units up, as I know, the horizontal translation must go inside the radical. So to go 7 left, I will actually go plus 7. So I remember the signs work opposite in there. To go 2 units up, I will add 2. Hopefully this has been helpful. Good night and good luck.